Hello and welcome to some chemistry. I'm Mr. Hicks, and today we're going to be studying limiting reactants. At the end of this, I hope that you should be able to understand conceptually what limiting reactants are through some real-life examples. You should be able to identify limiting reactants in a chemical reaction, and then you should be able to set up and solve limiting reactant problems. So let's talk about what this new word means here. Limiting reactant. That's the reactant, or sometimes known as a reagent, the things that you start with in a chemical reaction. And those substances that you start with get used up during the chemical reaction. Sometimes they aren't in equal amounts, or what we call stoichiometrically proportioned. And in that case, one of the reactants will run out first. And the one that does run out first stops the reaction and limits how much of the product we will actually get in the end. The excess reactant is the reactant that's left over. So of those starting substances, one of them may run out first, and then there'll be others that will be left over. We say that they're in excess because we still have enough there to make some more, but we're missing something to go along with it. Now, here's kind of a real-life example. Let's suppose we're making some books. And in the book, each of these needs to have a couple of covers, 20 pages of paper, and 3 staples to hold it all together. So you go over to the supply cabinet and you look in there and you see that there are 10 covers, 120 pages, and 75 staples. So we want to know how many books can we make. Now, in this problem, we have a couple of things. First of all, one of the things that we have here is we have kind of like our recipe to make a book, don't we? Now, I've referred to chemical reactions in the past as recipes, and it sort of is like a recipe in some way, and that's what this is right here. This is what this is simulating. This is sort of our recipe to make one book. All right, 2 covers, 20 pages, 3 staples. Down here, this is what we have in our supply cabinet. This is what we have. Here's what we need. This is what we have available to us, and we want to see how many books can we make. So for each of these 3 things that we have, we need to find out how many books can I make from each of these. So what I'm going to do is I'm going to do like a little proportion here to try and figure out how many books can I make. I'm going to set up a ratio or just do a quick division, right? I know that it takes 2 covers to make 1 book, so if I have 10 covers, how many books is that? Hear the proportion there? So I can just take the 10 covers that I have and divide that by the 2 covers that I need, and I'll find out that I can make 5 books from that. I'm going to do the same thing for each one of them. So I'll take the 120 pages of paper that I have and divide that by 20. And when I do that, I see, hey, I can make 6 books out of this. And then I'm going to take my 75 staples, and I'm going to divide it by the 3 that I need for each book. And I'm going to find out, hey, I can make 25 books from the staples that I have. Now, how many complete books can I actually make? 25, 6, or 5? Oh, I'll only be able to make 5 because I only have enough covers to make 5. So even though I have enough of the pages to make 6 books or enough staples to make 25 books, book production will stop when I hit 5. So you can see that our limiting reactant, the thing that's going to run out first, is going to be the covers. And it'll only allow me to make 5 books. Let's look at this process that we went through here. I first took a look at my recipe for making a reaction, Then I took a look at what I had. And then finally, I did some math to figure out for each one of the parts of my recipe to figure out how many of my product I can make from those. So that's kind of a real life example where we can get our brains around the idea of what a limiting reactant is. It's the thing that runs out first. How about we put this in terms of chemistry class? Because I know that someone's going to want you to be able to do this with some chemical stuff here, huh? So, how do I identify limiting reactants in chemical reactions? Well, we need to consider three things. First, the balanced equation. That's our recipe, isn't it? That's our recipe right down here. It says that in order to make this aluminum oxide over here, I'm going to need 4 aluminums and 3 oxygens in order to make this aluminum oxide. So this is telling us how much we need. Second thing we have to consider is how much we have of each thing. So the amount that we have, you'll find this in the problem itself. It's going to tell us, hey, I have 6 moles of aluminum and 6 moles of oxygen. Now I'm making this a nice problem right now, and I'm working in moles. You can work in moles or particles or liters to do the processes that it takes to figure this out. But you can never do it from masses, because masses are not like a particle, are they? Some particles are heavy, some particles are light, so the mass doesn't give us a true sense of how many we have, the number of something. So, the third thing we have to do is we have to do some math to figure out how much product can be made from each of these different reactants, the amounts we have and the amounts we need. So, here's what I do. You ready? I sit down with each one of these and I do myself a little bit of math. I set up a proportion just like we did before. The proportion here might be considered a molar ratio in some way, huh? But it's going to be a proportion. How much I have divided by how much I need. So, I know that I have 6 moles of aluminum, right? And I have 6 moles of oxygen. So 6 divided by 4 here, I think this comes out to 1.5, doesn't it? I took 6 divided by 4. 1.5 reactions I can make from this. 6 divided by 3, that's 2. I can make 2 reactions from that. So how many reactions can I go through? Well, each reaction I go through, is going to use up what I have in that. And so when I get through 1.5 reactions, that's it. The reaction's going to stop. Even though I have more oxygen and can go through 2 reactions here, I'm going to end up just stopping at 1.5 reactions worth of this. Now, if you wanted to know how much of the aluminum oxide you get, you could take this 1.5 and use that now over here. See, so I could say, all right, so I can do this 1.5 times. So 1.5 times my 2, what are you going to get up here? It's going to be 3. There we go. This is how we look at identifying what the limiting reactant is. We have to consider 3 things. The balanced equation, how much we need, the moles of the reactants, that's usually told to you, and then finally, how much of the product can be made from each of the reactants. Okay, so let's try to do a problem that is a true stoichiometry problem that you might find in a textbook, or that a chemist might have to do if he were working with something like this. Okay? So here I have some sulfur reacting with some chlorine, and it's going to make this sulfur dichloride compound. And just like in the previous problems, we're going to concern ourselves with a couple different things. first thing we're going to concern ourselves with is this balanced chemical equation, the recipe, right? And in the problem, we find the amounts that we have available, 200 grams of the sulfur and 100 grams of the chlorine. So what are we going to do? We're going to do the math, and we're going to do the math for each of these two starting substances to find out how much product each one will make. So step one, we're going to do some mass-to-mass stoichiometry, and we're going to do it twice, once for each of those substances. Then we can see how much product each of them will make, and we will choose the lesser amount of product to be the amount of product that can potentially be made from the limiting reactant. Okay, let's get on with it. So, one question that students many times have when they're working on this is they ask me, what am I solving for? Well, you're solving for the product, okay? The question will usually ask you how much of something will be, produced. And here it is, disulfur dichloride. How much of that's going to be produced? So that's what we're going to look for. And I'll set that up here. I want to look at how many grams of this disulfur dichloride will I make. And first, I'm going to find out how much I can make with the 200 grams of the sulfur. And then I will do it with the chlorine. So with the sulfur, first step, change it to moles. Now this is mass-to-mass stoichiometry. If you haven't done that yet, then I have a couple other stoichiometry videos in this series. There's a mole-to-mole, a mole-to-mass, and a mass-to-mass video. You might want to go check those out if you don't know what I'm going to be doing here with my stoichiometry. All right, so first thing to do is to change it to moles. So I'm going to put grams on the bottom. Cancel that out. And on the top, I'll put moles. 1 mole of my S8 sulfur. Why 1 mole? Not because of the coefficient up here, but because 1 mole of sulfur is equal to 256.8 grams. Where'd I get that from? Periodic table, 256.8. There we go. Next step is the molar ratio. The molar ratio, remember, is mole over mole. It's where you make the switch from one substance to another. So here we're going to be switching from the sulfur. I'll put that on the bottom to cancel it. And on the top, I'll put the disulfur dichloride. Then finally, I get the two numbers for this molar ratio from the balanced chemical equation. So I look at the coefficient for S8, and that's 1. And I look at the coefficient for my disulfur dichloride, that's a 4. Last step, since we're working in masses, let's find out how much this is going to weigh. So I'm going to put 1 mole of disulfur dichloride on the bottom, and on the top I'll change it to grams. That is 135.2 grams. When I work all that out on my calculator, I get 421 grams that can potentially be produced from the 200 grams of sulfur. But we're not done yet, because we were given a second amount of a starting substance, 100 grams of chlorine. So now I'm going to go through this whole process over again. I'm going to find out the number of grams of the sulfur dichloride. And again, this is something that sometimes confuses students a little bit, because they're like, well, what do I solve for? I already solved for that, that product. And the answer is you're going to solve for it again, just like we did with the books, right? We did it each time. We solved for how many books can I make, how many books can I make, and then we chose the one that was the smallest amount. So we're going to do the same thing here. So how much sulfur dichloride can I make from 100 grams of chlorine now? Same 3 steps. New molar ratio, because it's working with chlorine now. And then this should look familiar because this will look the same for both parts. Some chemistry teachers and some books in their examples may stop the process at the molar ratio temporarily. Have you figure out how many moles of product you're going to make and then just do this step once. I found that sometimes it's a bit easier if you just go ahead, do it twice, and then choose the lesser amount. So that's why I do it this way. As with anything in math, you know, there's multiple different ways of getting to the same place, isn't there? All right, and so for this one, I found out that it was 190 grams that I could make from the 100 grams of chlorine. So, now that I've done 2 mass-to-mass stoichiometry problems, one for each starting substance, now I can decide how much will I actually make. And for that, we're going to choose the lesser amount. The lesser amount in this case is 190 grams. And so that is the amount of product that I'll make. So that answers this question right here, 190 grams. And the answer to this question is going to be the chlorine, right? All right. Another point of confusion for some students is that they'll get these 2 numbers in the end, and it's just too simple for them to choose the smaller one. And so they'll try to do things like add them together, divide by 2, you know, all kinds of different variations that I've seen over the years. But you're going to be a smart one and just choose the one that is smaller. That's all we do. That's how you do this problem. 2 stoichiometry problems, pick the smaller amount, solve for the same product, and that is your limiting reactant. Okay. I bet that you might want to try and give this a whirl yourself. So, set up here is another limiting reactant stoichiometry problem. Why don't you press that pause button, give this a try, and when you're ready, I'll be here to show you how it's done, and hopefully you'll be able to do the victory dance. Okay, how'd you do? I bet you did all right, because you're probably getting pretty skilled at setting up these stoichiometry problems. All you have to do now is do it twice for this type of a problem, once for each starting substance, and then try and figure out which answer is the right answer. And we know that it's the one that is the lesser amount. That is the correct answer. Now, so that's what I did. I set up for both phosphorus and for the oxygen my mass-to-mass stoichiometry problems. I found out that for the phosphorus, I could make 57.3 grams. So, ding ding, there it is. That's going to be the amount that I can make, because once this phosphorus works it out so that it can make 57.3 grams, that's when the reaction is going to stop right there. So even though the oxygen had enough to make 88 grams, didn't have enough phosphorus to get there, so the reaction stopped at 57.3 grams. So my limiting reactant, it's the phosphorus. All right, well, that's it for me. What did we do today? Well, we figured out these new words, limiting reactants, saw a real-life conceptual idea of how to do it, figured out that we can use chemistry to kind of determine what is the limiting reactant, and then we set up some honest to goodness limiting reactant problems, the big kahunas of them all right there. And I bet you're going to do fine in your chemistry class with this because you're working hard and you're figuring things out. So that's it for me. I hope to see you again.